Hello, welcome everybody. Good afternoon here in Europe. My name is Ignacio Pagona-Barraga. I'm the current SICAM director, and it's a pleasure to welcome you on this installment of the SICAM Marvel Classics in Molecular and Materials Modeling series that is organized together by Marvel and SICAM. This is a periodic series of events where we invite the originators of methods and algorithms that have become a reference in our communities, so that we can listen from them how these methods and algorithms originated, what was the status at the time, and what have they brought, and how they have evolved and have impacted the way in which we do modeling and we understand materials around us. So these are events that, as I said, we organize periodically. You can come back to the one that we organized today if you want, because we store them in our platforms, and you can also watch previous ones. Here on the back of the slide, you can see the email, the addresses for Materials Cloud and for SICAM websites where you can find previous events, and then this one as well. So today we will listen about ab initio studies of electronic excitations using many-body perturbation theory, and we will listen this from the perspective and insight of Rex Scotby from University of York, Lucia Reining from the École Polytechnique in Palaiseau, and Stephen Louis from University of California, Berkeley, and Lawrence Berkeley National Lab. But before we move on, I wanted also to take the opportunity to talk about other type of events that both Marvel and SICAM organize periodically, and for which there will be installments in the near future. In particular, Marvel organizes on a monthly basis distinguished lectures, and the coming lecturers, as you can see here, in February will be Sharon Glotzer, who will be talking about the entropic bond. In March, Aspuro Gudzik from Toronto, who will be talking about materials acceleration platforms. And in April, Garnet Chang from Caltech. Title is still to be announced. The information about these events and also past ones, you can also find them in the Marvel website. You can find the address here. And also in SICAM, on a monthly basis, we organized what we call the Mixed Gen series. This is a series of events which take place online, which are addressed to PhD and postdocs, with the idea to address different topics relevant for modeling. And then they have a structure where there is a first part with a lecture provided by a well-established scientist, and then there are two additional lectures or talks by younger members of our community, and this is followed by a poster session to facilitate the interaction among younger participants and more experienced ones, and then even despite still we suffer from restrictions due to COVID to promote and facilitate scientific interaction in an informal environment. And again, you can find the specific information on the SICAM website. At the end of the month, there will be one installment about simulation quantum materials with Antoine Georges from the École Polytechnique as the experienced lecturer. And then in February, there will be one about glasses, simulating glasses with a lecture provided by Ludovic Broctier from Montpellier. And in March, there will be one event about simulating biological systems with the lecture provided by Benoit Roux. And on top of these periodic events, from time to time, we also organize specific ones. And in particular, in the coming month of February, we want to take note of the United Nations Day for Women and Girls in Science, to address the role of women scientists in modeling. And again, we will do that by organizing an online event with a non-standard format. We want to invite 4 scientists that are at different stages in their professional career to exchange about what is their experience and how they have gone through professionally in the area of computer simulations and modeling, that which is ours. So it will be a pleasure to count with Ruth Linden-Bell from Cambridge, Julia Galli from Chicago, Clement Cormibo from the EPFL, and Magali Benoit from Toulouse for such a discussion. And again, where there will be ample time for participants also to engage in this exchange of views and opinions. So again, the information about this event will be made public tomorrow in the SICAM webpage. So I also invite you to check about it, and then also to join us the 11th of February. So with this, I will just pass to, now we can pass to the event of today. I want to emphasize, I mean, this will become clearer next, but these events, these classics also have a slightly non-standard format, because there is a fraction of the event where we will listen to presentations by the three invited speakers. And then there is a second part that is a more informal discussion, where we also hope to get insight into what the actual, what does research mean, how they engage and how they live the development of this breakthrough, and also to get to know a bit more what is research for them and what does it mean working and contributing to modeling and the associated science. So I hope you will enjoy today's event, and it's a pleasure now to give the floor to Nicola Marzari, who is the coordinator of Marble, and who will be chairing the session today. So Nicola, now the floor is yours.
Thank you, Ignacio, and very warm welcome from me to everyone, and in particular to our three distinguished speakers today, Professor Rex Scotby, Professor Lucia Reining, and Professor Steve Louis, that have been really pioneers and practitioners among so many things of many-body perturbation theory. So as you see, the event is organized around 3 lectures, 30 minutes each. At the end of each lecture, there will be 10 minutes for question and answer. So all of you attending, you are very welcome to type your question in the question and answers pane, not in the chat, or to raise your hand, and I'll read the questions from the question and answers, or will give you access to the mic so you can ask the question live. And typically, because of time, we can't really answer all the questions, but we would be very keen to hear from you. And as someone has asked, everything is recorded, so you'll be able also to go back to this and watch it again on the SECAM and the Marvel web pages, and also on the YouTube pages. Okay, so without further ado, let me actually give the floor to the first lecture. It will be given by Professor Rex Scotby on underlying concepts and practical implementation of many-body perturbation theory. Rex is an emeritus professor of physics at the University of Oxford. His research has always been on the quantum dynamics of systems of interacting electrons, other complex systems, studies of the exact Kohn-Sham potential, especially in time-dependent density functional theory, and the development of improved approximate DDFT functionals for dynamical problems. Rex did his BA and PhD at the University of Cambridge, went for his postdoc at Bell Laboratories, and then came back to a faculty position at the University of Cambridge until 1995. That's where I met him. By the way, I was a PhD student at the time, and he moved to York in 1995. Among other things, he's also one of the founding members of the European Theoretical Spectroscopy Facility. Maybe we'll talk about that in the later part of our meeting, that evolved from other European collaboration. Rex, please, the floor is yours. A great pleasure to have you here.
Thank you, Nicola, and good afternoon from York. It's been a real pleasure over almost 40 years now to observe and occasionally contribute a little bit to the adoption of many-body perturbation theory techniques in ab initio electronic structure calculations. So I'm really delighted to have this opportunity today of helping to tell part of that story. It is, of course, a story to which the work of many dozens of researchers and latterly many hundreds of researchers have contributed. So let me share my screen. Okay, so here's an outline of what I'd like to say in my 30 minutes. I'll start by introducing the key ideas of many-body perturbation theory. I won't assume any prior knowledge of many-body perturbation theory. Then I'll move on to a particular approach within that theory, which is the GW approximation. Then I'll talk about two issues beyond GW. First of all, calculating the one-particle Green's function more accurately than GW allows, and also getting access to the two-particle Green's function. And then I'll finish with a few remarks on benchmarking of many-body perturbation theory, and some suggestions for further reading for any of you who wish to follow up these ideas. So the ideas of many-body perturbation theory. The aim of these calculations is essentially this. Given some complex system, a molecule or atom or solid, we want to get information about the electronic excited states of the system. So, for example, we might have this molecule shown here, and we might illuminate it with higher energy photons and look at the photoelectrons that come out as a function of their energy and momentum. That will allow us to build up the photo emission spectrum. We might illuminate the system with lower energy photons and look at how they're absorbed as a function of wavelength, the optical absorption spectrum. Indeed, we might connect the system up to an external field, for example, a voltage source, and look at the current that flows as a function of time. All those experimental techniques, indeed almost any conceivable experimental technique that involves electrons, is going to be exciting the electrons out of their ground state. So the aim of many-body perturbation theory is to provide as direct access as possible to information about those excited states. Okay, so turning that into a basic theoretical problem that we want to solve, we have a bunch of electrons moving around in the field of nuclei, which for the purpose of this talk, I shall regard as fixed nuclei. And of course, what makes that problem difficult is the fact that the electrons interact with one another, as well as interacting with the nuclei. That means that if we want to apply quantum mechanics in full to the system of n electrons, we need to solve the n-electron Schrödinger equation. We need to calculate the energies and wave functions of the n electrons. And of course, if you've ever thought about the object psi, which is a function of the positions and spins of n electrons, you'll know immediately that it's not conceivable that we could ever be able to calculate the many electron wave function for more than 5 or 6 or so electrons. We have to find an approach to the problem that is approximate, but hopefully is a good approximation for the quantities that we want to study. Okay, so by way of an overview that will give us some insight into many-body perturbation theory, if, as I think is true for many of you, you are already familiar with density functional theory. Let me just make a brief comparison between the two approaches. Density functional theory on the left, many-body perturbation theory on the right. As you all know, in density functional theory, Kohn-Sham density functional theory, we have a fictitious auxiliary system of non-interacting electrons, which move in an effective potential called the Kohn-Sham potential. And the Kohn-Sham potential is constructed so that the non-interacting electrons reproduce the exact electron density of our real system of interacting electrons. And of course, we normally decompose that Kohn-Sham potential into three parts: the external potential, which is the potential due to the nuclei; the Hartree potential, which is the classical electrostatic potential produced by the total electron density; and then this exchange correlation potential. And as you know, in density functional theory, you normally have to make a fairly ad hoc approximation for VXC, and for example, an LDA or a GGA, which has the feature that systematically improving that ad hoc approximation can be problematic. And in any case, access to excited state information in density functional theory is rather limited and rather difficult to get to. Now, in many-body perturbation theory on the right, we have a theory that's based not on the electron density, but on the electron Green's function, G. I'll be describing in a moment how that's defined for those of you who are not aware. And the theory starts from a set of exact equations obeyed by the Green's function and some other ancillary quantities that I've listed here. And what is striking for those of us who know density functional theory is that, in a sense, the concept of a system of non-interacting electrons moving in an effective potential also holds in many-body perturbation theory, as we shall see. The effective potential is the external potential plus the Hartree potential, and then plus this self-energy operator, sigma, which takes the place of the exchange correlation potential. And sigma is a non-local and energy-dependent potential. But like VXC, it is representing exchange and correlation within this many-body perturbation theory. And by the way, because we have an exact set of equations which are being solved by iteration, then that gives, in principle, a pathway to arbitrary systematic improvement of the theory. Okay, so what is this Green's function on which the many-body perturbation theory is founded? What I'm going to describe, strictly speaking, is called the one-particle Green's function, because it tells us what happens when we add one particle, for example, one electron or one hole, to our system. So let me build up the definition of the Green's function. We'll start with what I've written here is this wave function capital N, which simply stands for the ground state wave function of the n particle system. You can see it as this blue box here. Now, I emphasize that the theory is constructed in such a way that we don't need to ever calculate what this many-body wave function is. That would be completely defeating the point. But nevertheless, the definition of G is in terms of this quantity. So we're going to take our ground state wave function of the n-particle system, and we're going to add an electron at a particular position and time. Those of you who know the second quantization notation in quantum mechanics will recognize this operator psi hat, dagger, as a creation operator that creates an electron at a particular position and time. If you don't worry, because I'm going to try to give you a physical interpretation of what the Green's function is telling us. And then we're going to remove an electron at another position and a later time. So what we've just done is operate with the annihilation operator that destroys an electron at a particular position and time. And then we're going to take the inner product of the resulting wave function with the wave function that we started with, the ground state wave function of the system. So as usual, when you take an inner product in quantum mechanics, you're calculating a probability amplitude, a quantity whose modulus squared gives you a probability. And in this case, it's the probability for the added electron to have propagated from x prime to x as the time goes from t prime to t. So this is what the one particle Green's function is. It's a propagator for an added electron that takes into account the interactions between that electron and all the other electrons of the system. Okay, so this is how we just defined our Green's function in the top line. Now, it's quite easy to show using the exact definition of these creation and annihilation operators that this Green's function, if your system were to be composed of non-interacting electrons, would obey this equation. What we have here is simply the linear operator that would appear in a single particle time-dependent Schrödinger equation. Operating on the Green's function equals delta functions. Those of you who may have come across Green's functions in mathematical physics more generally will recognize this as the kind of equation that any Green's function obeys. So how is this relevant to us? We don't have a system of non-interacting electrons, we have a system of interacting electrons. Well, this is where we do something which is very much reminiscent of what is done in density functional theory. We say, let's define the effective potential in which our non-interacting electrons are moving, so that the Green's function G0 that satisfies this equation is in fact the full Green's function of our actual system of interacting electrons. And we're going to do that by creating an effective potential which is sufficiently rich to reproduce the Green's function that we want. Because the Green's function that we want is a function of 2 positions, 2 spins, and 2 times, then the effective potential also needs to be a function of 2 positions, 2 spins, and 2 times. And we will call the part of the effective potential that is beyond the external and the Hartree potential the self-energy operator. As I said before, this takes the place that VXC takes in density functional theory. It's describing exchange and correlation, but unlike VXC, it is a non-local potential and it's an energy-dependent potential. Okay. One of the questions that we might well want to ask of our Green's function, if we're able to calculate it, is what are the energies with which an electron can be added to the system? In an extended system, like a solid, the imaginary part of the Green's function looks something like these graphs here. If our system were to contain non-interacting electrons, that's shown in blue, we simply get a delta function peak at the energy of each single particle energy of the system with which an electron can be added or indeed subtracted. If we have an interacting system, that's shown in red, we have a richer behavior. The imaginary part of the Green's function is typically non-zero over a wide energy range, but typically it still retains this peak structure that is reminiscent of the delta functions that we have for non-interacting electrons. And what that means from an experimental point of view is that the system is showing approximate eigenstates that propagate as if they were non-interacting electrons. And these, of course, are what you would measure in a photoemission experiment or an inverse photoemission experiment. They form, for example, the band structure of a periodic solid. And from the definition of the Green's function, it's quite straightforward to show that if the spectral function, the imaginary part of the Green's function, has such a quasi-particle peak, then the energy at which that peak occurs, capital E, will satisfy this equation at the bottom. Now let's have a look at this equation. It's simply a single particle Schrödinger equation, kinetic energy plus potential operating on the wave function equals an energy. But taking into account that the self-energy that represents exchange and correlation is a non-local potential, so it has to operate in this integral fashion, this sort of matrix multiplication on the wave function. But again, we see a resonance with Kohn-Sham density functional theory. This is very much like the Kohn-Sham equation, an effective non-interacting Schrödinger equation that contains the effective potential that we're constructing so as to get out the information that we want. Okay, so in 1965, Lars Hedin showed that the self-energy and the Green's function that we've just defined can be cast into a series of closed equations that, most importantly, do not contain any reference to any many-body wave function, such as the n-particle ground state. So that gives us a way in to calculate the Green's function in a way that doesn't require us to calculate a function of 10 to the 23 variables, for example. These are Hedin's equations. They are integro differential equations. You can see that we're integrating over numerous spatial and time and spin coordinates. In the last equation, we've got a functional derivative, so they're integro differential equations, so they're a little bit nasty. Nevertheless, they are exact equations, and our task now is to solve these equations. So what have we got here? We've got the self-energy in the first equation. Then we have P. Well, P is defined by this equation, but one can readily show that it's equal to the irreducible polarizability of the system. Likewise, W is defined by this equation, but again, one can show that it's equal to the screened interaction between a pair of charges. And then we have this vertex function, gamma, which is rather complex. Okay, so how to solve these equations? Well, I just want to comment on the importance of focusing on W, the screened interaction. On the left of this picture, we see something very simple, an electron in blue, and we're going to bring up another electron shown in gray, and we're going to ask what is the potential energy of interaction of those two particles. Obviously, it's just Coulomb's law, 1 over r minus r prime. On the right, we see the same thing, an electron in the middle in blue, and we're going to bring up another charge, minus E, shown in gray, and ask what is the potential energy. But this time, the electron that we've put in is surrounded by all the other electrons with which it interacts. And of course, there are going to be rapid spatial and temporal oscillations of the surrounding electrons that will, on balance, tend to screen, in other words, reduce in strength, the potential produced by the original electron. That's a familiar concept, often described in physics through the dielectric function or the dielectric constant. And we're interested in that screening over all timescales, short and long, and over all length scales, short and long. But the point I want to make is that over almost all timescales and almost all length scales, screening is strong in molecules, atoms, and particularly in solids. Indeed, in metals, of course, we know that the dielectric constant after a long time has elapsed, in other words, at zero frequency, is actually infinite. But in all those systems, the dielectric screening is strong. That means that W is much weaker than the Baer-Coulomb interaction. And so it's a good quantity to try to make a perturbation theory in terms of, because it's going to be more convergent than the Baer interaction. Now the GW approximation. These are Hedin's equations that I've just written out more compactly than I had them before, just exactly the same equations written as sort of matrix equations. And we're going to solve them. This is what Hedin said. We're going to solve them iteratively, starting with sigma equals 0, on the basis that exchanging correlation, while it's of some importance, it's not as large as some of the other terms like kinetic energy and the interaction with the nuclei. We'll say more about that later, but let's just do what Hedin suggested. Start with sigma equals 0. If we look at the last of Hedin's equations, you see that gives a great simplification for this vertex function. It means that the last term just falls away, and the vertex function is the product of two delta functions, which we then insert into the equations for sigma and p. And then that means that the gamma here just integrates out, and we get p equals minus IgG, and sigma equals IWG. That last equation, sigma equals IWG, is the GW approximation. Writing it out more fully, you can see it's just a product of the Green's function and the screen-Coulomb interaction at a pair of positions, spins, and times. Like all these many-body quantities, it can be written as a Feynman diagram, as I've done here. These diagrams are very handy if you want to explore the effect of iterating the equations in a particular way. I'm not going to make any further use of them in this talk. But anyway, this is what the GW diagram would be. To interpret GW, notice that if W here were replaced by the Baer-Coulomb interaction, then we would have Hartree-Fock theory, Hartree-Fock exchange. So in effect, GW is like dynamically screened exchange. Now, a brief technical point, which I haven't time to explore in detail now, but we could, if you wish, discuss it further in the Q&A. It would be a disaster in practice to start a calculation with sigma equals 0 as in Hedin's exposition. That would correspond to Hartree theory, where we just say nothing is, well, exchanging correlation is going to be ignored completely. This will give you a terrible account of the electronic structure of almost any system. So in applying GW, one starts not from sigma equals 0, but from sigma equals an LDA potential or a GGA potential, or indeed a Hartree-Fock exchange operator, something that is already reasonably good at describing the electronic structure of the system and on which the equations can then more efficiently build. So this is what one does in the most basic kind of GW calculation. Let's look at this flowchart on the right. One starts, as I've just said, with an LDA or GGA or Hartree-Fock calculation of the electronic structure. That gives you a set of wave functions and energies. From those, you can form your initial guess for your Green's function. Let's call it G0. And then you can form, from Hadine's equations, the polarization propagator and the screened Coulomb interaction. And then you can combine the screened Coulomb interaction with G0 to form the self-energy operator. The star, incidentally, here denotes that, strictly speaking, there's a correction to the expressions for sigma and p that reflects the fact that we're not starting from Hartree theory, but from something much better than Hartree theory, like the LDA or the GGA. There's also the possibility of making the GW calculation self-consistent. That simply means recalculating the Green's function, updating that is to say, updating the Green's function, and then feeding that updated Green's function back into either the calculation of P and W, followed by sigma, or just into the calculation of sigma. And this loop can be iterated to self-consistency. Is that a good idea? Well, not necessarily. And once again, there isn't time to discuss it in the main talk, but if you like, we can talk about it a bit in the Q&A. So the early ab initio applications of GW focus mostly on the band structure of semiconductors and insulators, particularly the band gap. So, for example, in this graph on the right, you can see that the circular points, the black dots, which are the GW band gaps, lie pretty much on this 45-degree line, which is where they should be, and the LDA band gaps do not. Let's turn to some more recent benchmarks of GW for solids. Well, you can see the style has been continued. This is a very nice benchmarking study of GW for 80 different solids by Michiel van Zetten et al. And the green points are the GW band gaps, which once again lie fairly close to this 45-degree line, as they should do. And the red points are the, well, this time not LDA, but the GGA band gaps, which are way too small. What about molecules? Once again, we have some very, very nice benchmarking data. This comes from the studies of 100 molecules benchmarked by Caruso et al. And this is the ionization energy, the energy to remove an electron from the molecule, compared with very accurate results from configuration interaction quantum chemistry calculations, which are just about doable for molecules of this small to medium size. And the accuracy is reasonably good. And we also see here insight into the relative merits of different GW type approaches. But GW isn't just about quasiparticle energies. It's also about the spectral function. We see here on the left the spectral function of silicon. This is actually a slight enhancement to GW. It's GW plus what's called a cumulant, which gives a better description of the low energy satellites in the spectrum. You may hear more about that from Lucia later. On the right, we have the use of GW to calculate the charge density, the electronic charge density of the system, from which the corresponding VXC, exchange correlation potential of density functional theory, can be calculated, together with its own band gap.
Rex, let me mention the 30-minute mark.
Thank you, Nicola. So I'll just finish off now. So I thought I would try to give you some impression of the GW publications in the literature. As a way of gauging that, I've looked at the papers that cite Hedin's 1965 PhysRev paper. There are over 3,000 of them. And as you can see, it's running at around 250 papers per year. And you can see how the number of these papers started to take off, particularly after the first ab initio applications of GW in the mid-1980s. Just to mention very briefly, GW isn't everything. It's certainly not perfect. Sometimes you need information beyond GW, and some of the approaches that you may see mentioned in my colleagues' talks this afternoon would be a cumulant expansion. You can combine GW with dynamical mean field theory, which specializes in the short-range correlation that GW is not so strong on. And you can indeed include specific Feynman diagrams in the self-energy beyond GW, where you can argue that these are important for a particular application. Sometimes you want to just study things like optical absorption, where the measurement is much more naturally written in terms of the two-particle Green's function. That's the propagator for a pair of particles, let's say an electron and a hole. And you can develop many-body perturbation theory and in an analogous way for that. And what would correspond to the GW level of approximation would be GW plus what is called the beta-Salpeter equation. You may see that in my colleagues' talks later on. Okay, I will finish now. I just want to congratulate colleagues who have really started to seriously benchmark GW calculations, both for molecules and for solids. I think this effort has been started by Michiel van Zetten, Fabio Caruso, and Patrick Rinker. It's great to see that. And if you want to read further, there's a nice review article by Goals et al. 2019 in Frontiers in Chemistry. And of course, there's the wonderful book by Richard Martin, Lucia Reining, and David Seppeli, Interacting Electrons. So that's it. I will stop there and just display this summary. Thanks for listening.
Thank you, Rex. That was wonderful. Again, I invite people to write their questions in the question and answers or to raise their hand. Maybe I'll also start asking a question that is, you know, it's in the name. It's a many-body perturbation theory. And when you hear about perturbation theory, the first question is, you know, does it converge? Do we have an answer, an insight, or you know, will things go systematically better, or what are your thoughts, or what is known?
I think we still don't have a proof that it absolutely converges. What I can say, however, is that it's more likely to converge when you make a a perturbation theory in powers of the screened interaction than if you make it in powers of the bare interaction. So that's already part of the strength of Hedin's GW idea in the first place. But it's a good question, and I don't think we have a definitive answer.
Thanks. I'll pick some questions from the question and answers.
Yes.
And Raymond Amador asks you to comment on the computational cost of GW calculations and the scaling with respect to the number of atoms and electrons.
Yes. Okay, there are many different ways of implementing GW calculations, very much reflecting the same choices that you have to make in setting up a DFT calculation. You have to choose a basis set. You have to choose whether you're going to do an all-electron calculation or a calculation using pseudopotentials. In the case of GW, because the GW expression involves an integral over energies or frequencies, you have to decide how you're going to perform that integration. So the quick answer to your question, Raymond, is that the calculations are considerably more complicated than the corresponding DFT calculation, considerably more costly, because of the presence of non-local quantities and energy-dependent quantities, where the corresponding quantities in DFT would be local and energy independent. We made a contribution from my group some years ago called the space-time approach to performing GW calculations, which I think had a particularly good scaling. Admittedly, the prefactor of the scaling was quite large, so you had to be looking at a rather large system for the method to be appropriate. But I think that and its descendants are in use in some codes these days.
Thanks, Rex. Maybe I'll ask some other questions.
Yes.
Choices. And Lorenzo Sponza asked more about, self-consistency, when it is relevant and when it is not, and what are your thoughts?
Yes, it's a very interesting point. When one hears the term self-consistency, I think the implication is it must be a good thing. And to be sure, Hedin's equations, if we were able to get the exact solution to them, it would be a self-consistent solution in the sense that the G that appeared in every equation was the same G, and the sigma was the same sigma, and so on. But what we're talking about here is not a full solution of Hedin's equations. It's an application of GW only in a self-consistent way, such that the G and the W, so that the G and the W that form the self-energy sigma are composed from the Green's function that comes out from sigma, as I described earlier. Now, that's not necessarily a good idea, because what you're doing there is you're iterating a selection of Hedin's equations, but you're not iterating the equation for the vertex function. The vertex function in particular contains this functional derivative of sigma with respect to G, which would be extremely difficult to do. And because you're not iterating the vertex function, you run the risk of including terms of a given order in, let's say, W, in a partial manner. And that can be a very bad idea, because you may be missing out important cancellations. So in summary, yes, if you're solving Hedin's equations in full, you must be self-consistent. But if you're sticking at the level of GW, it may not be such a good idea. And there's evidence that, for example, fully self-consistent GW, particularly for extended systems and particularly for metallic systems, is actually quite a bad idea.
Thanks, Rex. And maybe I'll ask a last question that is coming both from Vietan Ha and Domenico Corona. And they ask, what about, strong correlations? After all, we know or we assume that GW doesn't work well for that kind of systems. And why is it the case, and where is the problem?
Yes, GW is very good at describing long-range correlations. We've seen that it includes very centrally the screening, the dynamical screening of the Coulomb interaction, which is particularly relevant at long distances. What it does not include so well are correlations that are relevant on, for example, the D shell or the F shell of D or F elements. But of course, they can be nicely described by dynamical mean field theory. So as I mentioned very, very briefly, some groups, I think Silke Biermann was one of the first authors of that work, have endeavored to combine DMFT with GW, which is great, but you have to be very careful not to double count physical effects. But I think they figured out how to do that.
Great, thanks, Rex. Actually, we will have a second Marvel Classics on dynamical mean field theory in the fall, so that's very appropriate. I think in the interest of time and to keep everything, I think we'll also go to the next talk, but thanks a lot. It was a great pleasure to have you here, and we'll talk more later. So with this, let me also introduce our second speaker today, Professor Lucia Reining from École Polytechnique in Paris, on electronic excitations in a many-body world from quasi-particle to spectra. And Lucia is an exceptional grade senior researcher at CNRS, that's the National Research Council in France. She did her master degree at Aachen in Germany with a pen and paper thesis, but then moved to Tor Vergata University in Rome to work with the much missed Rodolfo Del Sole, where she got into computational physics. And so she did a PhD in many-body perturbation theory, first rooted in tight binding methods, but then moved on to actually starting from first principle calculation. Very appropriately, after her PhD, she moved to SECAM, actually, so with a Marie Curie fellowship. SECAM at the time was located at Orsay, after the foundation in 1969 by Moser, and she really sort of focused on GW from first principle. As it was mentioned for Rex, very much initiating this European theoretical spectroscopy facility, the TSF, that we'll hear more about later. And she also started moving on to the solution on top of GW of the Bethe-Salpeter equation. So she has been working on development of density functional, Green's function, functional, approximation and application. The beautiful book together with Richard Martin and David Sepperly, that I think is actually in the audience today, on interacting electrons, is a great starting point to go deeper into this field. She has gotten a silver medal from the CNRS. She's an APS fellow, an ERC advanced grantee, and she had also the Gentner-Kastler Prize of the French and German Physical Societies. With this, Lucia, also a very, very great pleasure to have you here, and the floor is yours, and I'll start the timer.
Thank you very much. Yeah, it's great to be here and to look a little bit back and look a little bit forward on the field. And it's a pleasure to illustrate some things with thoughts and results that we had over the year with friends in the Palaiseau Theoretical Spectroscopy Facility and elsewhere over the world, in particular in the European Theoretical Spectroscopy Facility, and also with many, many collaborations and many discussions, including with Rex and Steve. So I decided to put forward an aspect that is, of course, very important from the start in this business of many-body perturbation theory, but that has maybe attracted more attention more recently, and which is to go from quasi-particle band structures to whole spectra. And my talk will take you through a discussion, a sort of a sketchy discussion of what is a frequency-dependent Hamiltonian, where does it come from, what does it mean, what are the consequences, link this to experimental observations, put the GW approximation into that context, and interpret it as an electron boson problem, which will then also take me to going beyond GW with cumulant Green's functions, and I will finally extend the discussion to the electron-hole problem. And if I have time, I will also talk about this question of what is missing in GW and how could we go beyond. So Rex has already started from the many-body Hamiltonian. So in a system that has not a time-dependent external potential, this is a perfectly static Hamiltonian. And if you then decide to do density functional theory because the many-body problem is too tough, you again end up with a static equation, which is the Kohn-Sham equation, which I've put here. It is a simple equation, one electron equation with an effective potential that is static and local. But if you move on, and if you go to many-body perturbation theory, you find effective Schrödinger equations like this one. Rex has also shown it. It has the same kinetic energy, external potential, and the Hartree potential as the Kohn-Sham equations, but then you will find a frequency-dependent effective potential. So this is a non-local potential, and this is a remnant of Hartree-Fock, of course, of the exchange, and everything depends on frequency. Now, you could say, but why? How comes that from a perfectly static problem, I end up with a frequency-dependent problem, and in a way that is in principle exact? I think it's worthwhile to look into that. And to understand, let us take a simple 2x2 problem. So we have a 2x2 Hamiltonian matrix. We have an eigenvector with two components. And of course, this will have two solutions, omega, as eigenvalues. Now we can write this as two linear equations that are, of course, coupled. And suppose we are only interested in the first component of this eigenvector. Then we can solve the second equation for the second component, phi2, and we can put it back into the first equation. And then we find a unique equation for phi1. Now, you see that the Hamiltonian, the effective Hamiltonian governing this phi1, has the part S, which was the upper left part in your Hamiltonian matrix, is the 1,1 part, the one that should be dominant for phi1. And then you have a correction, and that correction brings in frequency dependence. And of course, if you first look at the equation, you may wonder, because now we have one equation, one component, you would have just one solution. But because the Hamiltonian is frequency dependent, you still have your two solutions of the original equation. So a frequency dependent Hamiltonian has more solutions than a static Hamiltonian, and it hides the rest. And that is something that you can see here. So in this frequency-dependent part of the effective Hamiltonian, you have all the part of the matrix that were not S, the rest that you would somehow like to describe in an efficient way. The question is then, in our problem, in our spectroscopy, what are these more solutions? And what is the rest in our problem? So our problem is, for example, photoemission. You come on with a photon, you kick out an electron from the sample, you measure its kinetic energy, you can do this angle resolved, and then you get, for example, a map of the band structure as for germanium on the right side. A band structure is actually a single electron picture. It means that you imagine that an electron in the material, every electron has its energy, and when you kick it out, it comes out with its energy. And this means that you get a series of sharp peaks that might disperse with a wave vector k here. What happens in reality when you kick out an electron from a system? Well, this electron, when it goes out, it leaves a hole. This is a perturbation. The system is no longer in its initial n-electron ground state. And this is a sudden perturbation. So you hammer on the system in a way, and the system reacts. And when the system reacts, this can make waves, it can make oscillations. They take energy. And it means that when you now measure your photoelectron, it will come out with less energy because it has left energy in the system. And therefore, the photoemission spectrum of an interacting system is like the one I show on the right side, and Rex has already shown something like that. It has these sharp peaks. They are now more broadened usually, and it has additional structures here. And these are satellites. We call them satellites or sidebands. And these express the fact that you have left energy in the system. When you came out, you electron, and therefore this energy is given to excitations of the system. So these are explicit many-body effects. This is not something you can get with any static Hamiltonian because it's additional solutions. To have more solutions, you need frequency dependence in your Hamiltonian. And it expresses, as you have just seen, a coupling of excitations. So this is the meaning in our case, and that is where the frequency dependence comes from. And you can have a simple image of this to understand better, which is an electron-boson coupling. So you have an electron on some level in your system, and it's coupled to bosons. These are excitations of the system. So here we have a single electron level and the boson coupling, and the boson here, and this is the boson. And the spectral function of this exactly solvable Hamiltonian is a series of structures, delta functions, sharp structures. You have here the energy of a quasi-particle. It's the original energy of your level here, shifted because of the coupling to the bosons. And then you have n, where n is some integer number, satellites, and these are at the bosonic energies. That's the exact solution. And that corresponds, here is sort of a picture of the exact solution of this Hamiltonian. So you have a quasi-particle, and then you have satellites. And this actually reminds you of the picture I've shown you before. You have these quasi-particles and the satellite structure that contain these bosonic excitations. And another image for this is a boat that goes on the water. So the electron is the boat propagating in the medium. This is the quasi-particle. And then you have, of course, the fact that when you propagate on the water reacts and makes waves, and these give rise to your satellites. Experimentally, this is what is observed. This, for example, is bulk aluminum, and we have a GW band structure on the left side and an experimentally measured band structure on the right side. So we have K points on the x-axis and binding energy on the y-axis. And this has been performed at the Swiss light source, this experiment. So simple metal. And if you look further down at binding energy, which people often don't do, and which, especially in the beginning of GW calculations, people would never do, you see in the experiment very strong additional structures, replica of these bands, and they are actually at a distance of the plasmon energy of bulk aluminum. So these are the additional excitations, the additional plasmons that give rise to this replica. And the same in bulk silicon. And this is measurement at the Soleil synchrotron. And you have here the bands of silicon turned down, so 90-degree turned down. And this is the band structure part. The blue crosses are the experiment. And the first 12 electron volt are band structure. And all the rest are additional structures, satellites that are only due to these explicit many-body effects due to a frequency-dependent Hamiltonian. And this actually fits nicely to my previous picture of the one electron boson coupling model, only that in silicon, of course, this is angle integrated photoemission. So you have a lot of quasi-particles here. And so also the satellites are a lot broader. Okay, you can crank the interaction strength up when you go in your electron boson model. And if you crank it up, you shift more and more weight to the satellites. The quasi-particle finally disappears. In this picture here, it would be about here. The quasi-particle is completely gone, and you pile up all the weight in the satellites. And this way you can, for example, open a gap. And this might remind you this correlated oxides. This is a very historical measurement. It has been redone, and there are new results, of course, but I still keep this historical picture by Fujimori et al. And you can see that in a series of oxides going to stronger and stronger correlation, you completely destroy the quasi-particle and you put all the weight in these satellites. So what about GW? As we have seen, we have a time difference dependent or frequency dependent self-energy, and that's logical because coming from Hartree-Fock, as I said, Hartree-Fock is sort of a starting point of GW. In Hartree-Fock, the electrons are frozen. This is a really rigid approximation. It's like instead of being on water, you are now ice skating, and the material does not react at all to the propagation of the electron. And if you go to GW, this is really the boat on the water picture because the material reacts through this screened Coulomb interaction. This is the difference to Hartree-Fock, as Rex has pointed out, and the frequency dependence comes from the dynamic screening, the inverse dielectric function. And this is where what I called the rest is hidden, because the imaginary part of the inverse dielectric function is proportional to the loss function. And there you see all the excitations of the system that you can measure, for example, with electron energy loss or inelastic X-ray scattering. And so this is where the rest is. And also in the case of silicon, these are excitations that you could measure in the loss function, and these are the plasmons. Silicon plasmon energy is about 17 eV, and that's right, the distance that you find here in the experiment. So the GW has these bosonic excitations, and so we can think that this is a really good electron boson Hamiltonian in a way. Now, it's not because you have a very good electron boson Hamiltonian that you also have a very good solution of this electron boson Hamiltonian. For now, we have just said probably GW has a very good Hamiltonian. So what about the solution? So do we get this series of peaks that we should get in the spectral function? And that would be all the waves that I can produce. We have tried this out. And instead of taking the one level electron boson coupling model, we took a 2-level model, which you can find, for example, in a publication by Gunnarsson, Meeden, and Schönhammer. But this doesn't make any difference for our purpose here. And this is the exact solution of this model. It has been recalculated by Sky Zhu, his PhD thesis. And what we have here is as a function of coupling strength. So here this coupling strength goes up, and the so-called quasi-particle renormalization factor Z goes down. But let's say from left to right is increasing coupling strength. Here is energy. And you have all the levels as a function of coupling strength. And you see that the first level is your quasi-particle, and then you have the satellites. Now, if you want a spectral function, you decide your coupling strength. You draw a vertical line, and you see the quasi-particle peak, first satellite, second satellite, and so on. And this is what I have put on the right side for a coupling strength, a Z factor about 0.8, which corresponds to silicon. And that's the picture I've already shown you. So that's what you want to find. And that's what experiment actually measures. This is the GW solution of this model. You see, it's very, very different. It's very different. So same model, same Hamiltonian, very different result. And if you take a spectral function, you see that actually in the quasi-particle region, GW is good. But if you go down, let's say this is an illustration. So this is silicon in the quasi-particle region, and crosses are experiment, blue, GW is in red. And as we know from all the band structure calculation, the quasi-particles are well described in GW. So now we make this region larger, and we go down in the satellite region where all the satellites sit in the exact solution. In GW, there's only one satellite, and it's further away from the quasi-particle than the first satellite in the exact solution. So you cannot even think this is the first satellite. It's a sort of average satellite. And that's exactly what we'll find in a GW calculation. So again, in red, GW, in blue, the experimental satellite series. In GW, a sort of one average satellite. This is really a typical GW result, and this is why people usually said GW is not good for satellites. So we have the good physics, at least for silicon, the good Hamiltonian, but when we solve the Hamiltonian, we make a low order approximation. And so we have to look for a better solution of the same physics problem. So how do we do actually perturbation theory? We do perturbation theory by looking at the Dyson equation, where we have the classical, the Hartree-Green's function, and we have a self-energy that is a correction, the integral kernel in the Dyson equation. We can write this as the solution of the Dyson equation is the classical, the Hartree-Green's function, and it's corrected by some factor. And it's here that we do perturbation theory. It's the self-energy that we take to first order in W. But we could write down an infinite number of ways to correct the Hartree-Green's function. And we can do this, of course, getting inspiration from models, from exact properties of the wave function, and from many different fields. And a very good way to post a correction is this cumulant form, where you have the Hartree-Green's function, and at equal time distance, we have an exponential correction factor. And it's this C in the cumulant, the exponent, that we want to approximate. And this is just doing perturbation theory, but on a different object. And we have been working on this and on the question of how to write down this and how to make it systematic for quite a while. So now, instead of having the self-energy linear in W, we make a linear in W approximation to this C function. And of course, if you have an even linear in W approximation to C, when you expand the exponential, you will get a series that is of all orders in W. Like when you expand the Dyson equation, you get results of all orders in W. So a very important remark is when you do perturbation theory, it's not only to which order you go in what you expand, but also what is the object that you expand that can make a lot difference. Okay, of course, cumulant expansion is a very old topic. We didn't invent this. It goes back to the 60s, at least. The cumulant idea itself is even older, of course. And there's very many important works by Jerry Mahan, for example, by Hedin. First ab initio calculations, I would say, are by Ferdi Aristatiaban on sodium. There has also been done silicon. It has been adopted also in the context of DMFT, so it's really widely used, and each of us has brought other aspects to the problem. Here I show you the cumulant solution for the same model that we have just been looking at in GW. You see at first sight, it looks much, much better than GW. It has this series of levels of satellites. It's not the exact solution for the two-level model. It's the exact solution for the one-level model, but not for the two-level model. But it's still a very, very good solution for the electron removal part. You can see it if you look in this window. And therefore, also when you do your ab initio calculation here for silicon, and that's the PhD work of Matteo Guzzo, you will find the green curve. So the green curve, very good band structure like GW. Also, all the satellites are here. Okay. There is still intensity missing with respect to experiment. This is actually not a correlation effect. It's due to differences between theory and experiment. I might come to this in a moment. If you add these, you get the black curve, which is in very good agreement with experiment. And silicon and the cumulant expansion for silicon has been studied also by other groups. We had a common interest in this thing over the years. So there is work also by Steve Louie and co-workers, by Johannes Lischner, Fabio Caruso, with Feliciano Giustino. So many of us have been re-looking at this. For example, they looked at the angular dependence of the satellites, and there's still a lot of work to do. So again, same on bulk aluminum. Bulk aluminum, we had this satellite series in the experiment. And when we do the intrinsic cumulant calculation, we also get the satellite series. And there's intensity missing with respect to experiment, like before. We can actually add it again, like we did in silicon. This is a parameter-free calculation besides the secondary electron background. And you see that now this is the new result, the GW plus cumulant plus plus, which means plus things in the experiment. Very, very good, even quantitative agreement with experiment. So what we have to add here is essentially the fact that we are even at 35 Kelvin, not at zero temperature. And so atoms move, we lose momentum conservation. This we have to take into account, gives you dispersionless features. And we have the outgoing photoelectron, so not the intrinsic spectral function of the hole, but the outgoing photoelectron on its way to the detector. It makes additional scattering, and this gives additional plasmon satellite intensity with extrinsic and interference effects, and that's actually what gives us the final spectrum. Okay, so what about going beyond the one-body Green's function to the electron-hole problem? An electron-hole problem appears when you do experiments like absorption. So now you take your electron, you don't kick it out of the sample, you just excite it somewhere in the sample. And this means that now you have to deal with the hole and the electron together. The hole is dressed in the sense that it excites the system, it's screened, the electron idem. And so you have a two-particle problem of two interacting particles. If you write down your density response function, your electron hole correlation function, of course, it contains a part that is the hole, G, and another G for the electron. But the two are not independent. There's an electron hole interaction. And this interaction actually comes from the fact that when you excite your system, all the potentials change because your Hartree potential depends on the density, hence on the Green's function. Your exchange correlation self-energy, which is an effective potential, depends on the Green's function. And so this change of potential gives an effective interaction. And this leads to the Bethe-Salpeter equation, which is like the Dyson equation for the one-body Green's function, now a Dyson equation for a two-body correlation function with this electron hole, independent electron hole part L0, and the interaction kernel that comes from changes in the potential. And if we use the GW approximation for the exchange correlation self-energy, the derivative gives us just an attractive screened Coulomb interaction, and the Hartree gives us a repulsive bare Coulomb interaction. So that is what we usually use. Moreover, we make the approximation that even the screened Coulomb interaction in this context is instantaneous, no frequency dependence. That's the standard approximation that almost everyone does. This way of doing and of solving the problem for a real system goes back also to early work. In particular, I would like to cite Hanke and Schramm, even in the 70s, also very important work by Strinati. All these works were done in semi-empirical way, but there were a lot of understanding and a lot of interesting suggestions of how to solve the problem. We have then taken this up later in the 90s with Giovanni Onida and Rodolfo Del Sole, Vanna Andreoni, and with Rex. And this was probably the first fully ab initio calculation for a small cluster. And then we moved to solids. And actually, we were not alone, because it happens very often in physics or in science that there is something in the air. You know, something is ripe to be done. And so different groups, even independently or talking very little to each other, move along essentially in the same moment. And this is, therefore, it's not astonishing that all the work on solids, we were all more or less at the same time in Europe and in the US, and in particular, Steve Louis and also Eric Shirley. Okay, today, Bethe-Salpeter in this form, with this kind of approximation, is, I would say, quite routinely done. And just for illustration, this is a work that's not even yet published by Vitaly Gorelov, and with a lot of collaboration also with Experiment, with Martin Feneberg and Rüdiger Goldhahn. And so V2O5 is a layered bulk material. It's an oxide. It's interesting. It has some applications, for example, in photovoltaics. And if you look at a typical situation of an absorption spectrum, so Vitaly calculated GW band structure. From this, he got the absorption spectrum in the random phase approximation, so without electron hole interaction. That's the continuous, the dashed, and then with some Hartree contribution, the continuous orange curve. And if you now switch on this attractive electron hole interaction, typical observation is a lot of intensity goes to the low energy side. We have a huge shift of the spectrum and a huge increase of oscillator strength on the low energy side. So this is called a bound exciton, where you had a gap before. There is now a structure, and it's a binding energy of more than an eV. And there's actually even stronger bound exciton here, where you have the little arrow. This is a so-called dark exciton, which you cannot see in optical absorption, but it's there. And this spectrum that Vitaly has calculated is actually in very good agreement with the ellipsometry that was done by Feynman and Goldhan. That's a typical situation. Also, typical analysis is you sit on this exciton and you say, okay, this is a two-particle problem. It means that electron and hole are correlated. So if I say, suppose I put my hole on the bridge oxygen, where actually it essentially wants to stay, where does the electron go? It's attracted. And indeed, if you look at these two pictures, so this is the bright exciton, so this peak, and this is the dark exciton. You see that the electron goes towards the hole. It wants to stay close to the hole because of the attractive interaction. In this case, it's actually surprising that it's not so close, because with a binding energy of more than EV, you would expect a Frankel picture where it's completely atomic-like, where everything is clustered together. This is not the case. And it also shows you, this shows you that you need ab initio calculation if you really want to have a realistic description of the material. The simple models for the materials we're interested in today are not sufficient. They can help to understand some things, but not everything. So we have now excitons beyond textbook models. There are many examples, but we didn't include the dynamical screening. So what about dynamical screening? No one does it, so don't we need it? Why don't we need it? We have been looking into this with Pierluigi Cudazzo, and we have said, okay, let's treat this full problem with dynamical screening. Dynamical screening for the hole, dynamical screening for the electron, dynamical screening for the electron-hole interaction. So I should say that we have immediately moved to the cumulant description for this, because from the one-body Green's function, we learned that doing perturbation theory on the level of the Dyson equation to get satellites is not a good idea. So we said, let's immediately do cumulant. So we formulated this problem in terms of cumulants, it's quite heavy equations, and we applied it to a Wannier model just to show what happens. And in particular, we looked at the 1s quasi-particle of the Wannier and its satellites. So it's just one transition here or here. This is the quasi-particle, and this is the satellite that for a quite strong interaction in this model we get. So there's a satellite series. And what is interesting is if you analyze these satellites, you find that actually they have positive contributions here, the continuous, and negative contributions here, for example. And because they add up, at the end, they are not so strong. And you can, of course, understand it because we have in this system, let's say we make an exciton, the exciton makes other excitations in the system. They can be, again, excitons. There are other electron-hole pairs. And so we have electrons interacting with electrons. This is repulsive. Electrons interacting with holes. This is attractive. And we have all the signs and all mixtures of signs. And so there is a lot of cancellation. And this has already been discussed for the quasi-particle and its broadening itself. For example, in the work of Friedheim-Beckstedt a long time ago, and also for core levels by Carstairs and Curtis. And because we have these positive and negative contributions, usually we can neglect them. We can neglect the dynamical screening. Also, you might see that these satellites are on the high energy side. So if you imagine you do absorption, you have satellites higher up. Often they fall into the continuum, you wouldn't even notice. But of course, they might still be important. And there are situations where this will be important. And there are situations where you can see it experimentally. This is the inelastic X-ray scattering, the dynamic structure factor of aluminum by Sternemann and collaborators. And you have here different curves for different momentum transfer from the pink low momentum transfer to the black high momentum transfer. This is the dominant plasmon, which becomes much broader at large momentum transfer when it enters the electron-hole continuum. And you have a little bump here. And if you look, for example, at the red curve and the black line, which is a guide to the eye, you see the bump more closely. And this is at the double plasmon energy. So this is the double plasmon satellite of the plasmon in the dynamic structure factor of sodium. This has been treated diagrammatically by Sturm and Gusarow for the homogeneous electron gas. And you can also do it for curiosity in time-dependent density functional theory if you have a frequency-dependent exchange correlation kernel in that case for TDDFT. Again, frequency dependence, more solutions. You can also get the double plasmon in that way. Yeah, that brings me to the last point, because it all seems so nice. So what are we missing? To understand this, let's look at the problem again. Our problem is, let's say, photo emission. So we have a box full of electrons. We kick out an electron with a given spin, sigma prime. And because we do this perturbation on the system excites and makes a lot of electron-hole pairs, which can have the same or different spin. And this is a full many-body problem. We should treat this all together. We are not able to do it. And so we cut the problem into pieces. And we say, okay, all these electron-hole pairs that are created, they give us W. And this W, we treat it completely independently of the photo emission process. It's the W of our system. And we separate it from this outgoing electron or quasi-electron. This is what we do in GW. And there is
mention also the 30-minute mark.
Yeah, almost finished. This is our boat on the water picture and all these excitations that are in W. But no one tells you that you have to cut the problem like this. You could also cut it, for example, like that. And that means that the two holes are now talking together and are correlated. And the electron has a different role. Or you could correlate electron and hole of different spins, and this gives you different approximations. This is a whole class of diagrammatic approximations that are called T-matrix approximations that have also been discussed, of course, and have also been studied in ab initio work. And I put you a few typical references of other people here. And finally, we have to go beyond electron boson coupling, putting more particles together. You can do three-body scattering, for example. I also put you a reference of Calandra and Mangi. Or you could say, well, when I kick out the electron, the excitation, the system is changed. So I have to change the boson. The boson is no longer fixed. And this gives you, of course, brings you to a nonlinear response. And we have been looking into this, for example, with Marilena Zavala, Josh Kath, and John Rea for core levels. And it actually gives important contributions to the solution for small systems. Okay, and that's my summary. That's all the points I wanted to talk to you. I would just like to, again, stress the fact that correlation is not everything. Exchange correlation is not everything. There is a gap between theory and experiment, and be careful before putting too much, just giving too much fault to the correlation if you don't fit experiment. Small models are very, very important to understand a few things. And yeah, with this, I thank you for attention. I'm ready for questions.
Thank you, Lucia. That was wonderful. Again, questions in the question and answers pane, or just raise your hand. Of course, I can't resist, starting with a question that is, if I think at, quantum chemistry and condensed matter computational physics, one went, the way of perturbation theory, Monolayer, couple cluster, and so on. And the second, at the end, developed very much around the density functional theory for the ground state. And, looking at many-body perturbation theory, it feels that, again, we have diagrammatic techniques that, add excitations, add complexity. But what are your thoughts these days about having functional theories towards, electronic excitations?
Okay, so it depends what you mean by functional theories. I would first of all say that this is already a functional theory in the sense that we express our observables as functionals, explicit functionals of the one-body Green's function or the two-body Green's function, right? Often when people say functional theories, they think about variational functionals, like starting from an energy and, okay, designing the energy functional, from this getting for example, a Green's function. That's a different question. That's a different question. So, of course, you can calculate energies, total energy, the ground potential, using Green's functions and using many-body perturbation theory. And there are many different functionals. You will people talk about the Latinger-Ward functional, the Klein functional, so different ways to express the total energy. There's also the Galitsky-Migdal formula for the total energy. Then the question is this variational in the sense that if I minimize, do I get a physical solution? for example, the Galitsky-Migdal formula, you cannot perform this minimization, but the Latinger word functional, that's different, okay? But that's a really different question, is do I have a variational, and should I use a variational energy functional, and do I express my observables as functionals, explicit functionals of the one-body Green's function? It's different.
Thanks, Lucia. I'll take questions from the question and answer. So Lorenzo Sponza says, you know, in your model where you compared exact versus GW versus cumulant, I noticed two things. Both GW and cumulant are less reliable in the strong coupling regime. What are they missing, given that the exact model is very simple?
Okay, here it's clear because we have postulated our Hamiltonian, okay? So let us again distinguish this. In this model, we have postulated the Hamiltonian. This means that the only error is in the solution. And as I said, this is perturbation theory. GW is a first order approximation to the self-energy that you also have in this model. The cumulant solution is a first order approximation to this exponent, okay? But both are first order approximations. And because they are first order approximations, when you go to high coupling strength, first order is not enough. That's very clear. But you should not forget that in a real system, if we crank up the interaction strength, we do this by changing the system, okay? You change the Hamiltonian. Here we don't change the Hamiltonian. We change the coupling strength, but let's say we know that the Hamiltonian is correct. But in the real system, as I said, the GW corresponds to Hamiltonian. That is a sort of coupling between a hole and all the neutral excitations of the system. And this is already per se a choice, an approximation. And especially for the strongly correlated systems, you have low energy excitations, like spin flip excitations, that are not in W, okay? So even your Hamiltonian would not be sufficient.
Thanks.
So we have to distinguish this.
And to stay on this, Lucia, you see the cumulant solution gives these little white satellites above the quasi-particle energy. Where are they coming from?
This was a test for your eyes, Nicola, and you passed the test.
It's Lorenzo, actually, so...
Aha, okay. I have cut this picture because this picture has also another side up there. And because we have here an electron on a two-level model, we can add and remove electrons, okay? So we also have an electron addition side. And I haven't shown it because it's not pertinent for photoemission, would be pertinent for inverse photoemission. And there we have a lot more problems with the cumulant solution. I would have loved to talk about this. It's nice that you bring me to it. So the cumulant solution looks very, very good for this electron removal. But if you go to the electron addition part, the cumulant done in this way does actually have problems, and we have to work more on that.
Okay, let me ask a few more questions. So we have Ali Kuchukalic that asks about magnons. Can one find satellite amplitudes in a magnon spectrum? Is there an analogy there?
Yes. So let me immediately put up a reference that I have done a little quickly. So this T matrix approximations, okay? Here you can, so when you want a magnon is an excitation that's not contained in W either, but it's still a bosonic excitation. So it means that when we decided to couple to all these electron-hole excitations, we neglected the magnon, so we have to move to such a picture. And actually there is nice work by Nabok-Blügel and Christoph Friedrich of 2021, where you can find this electron-magnon coupling, and you will find that this makes satellites, and this is by GW plus GT, which means that here T is the T matrix. So you have this kind of excitations, you can add that.
Thanks, Lucia. And now we go to the Bethe-Salpeter. So what about the different spin channels and the spin orbit coupling in the spectrum? How are these taken into account?
Okay, so in what I showed you, I didn't talk about spin at all. But people have been, of course, looking into spin-dependent problems for a long time. There is, for example, a very nice article by Claudia Rödel with Friedhelm Bechstedt, where they really write it down very carefully. And of course, also, if you look, for example, at the review of in the year 2000 of Michael Rolfing and Steve Louis, if I remember well, there's also quite some discussion on the spin problem. And also, of course, if you go back to the old papers, Hanke, Sham, Strinati, you will find useful input about spin. Spin orbit coupling is more complicated. It's often included in some perturbative way or in the pseudopotentials or different ways. But I think there is still, on one side, quite some things to do. On the other side, insight that can be schematized very easily. I mean, it's going from no spin to some spin-dependent insight is not so complicated.
Thanks. And then Domenico Corona asks, in which way the Bethe-Salpeter equation is better than time-dependent DFT, or what is the relation between those in terms of neutral excitations?
Okay, let's see what better means. So in principle, if you write the full Bethe-Salpeter equation, so let me go back. Okay, if you're interested in the two-particle correlation function and you write this equation, which I called Bethe-Salpeter equation, if you had the exact self-energy and the exact one-body Green's function, you have the exact equation and you get the exact result. And there is also an exact Dyson-like screening equation, linear response, TDDFT. So there are two exact equations. There are two differences. The first difference is this is an electron-hole equation, which means you have the propagation of an electron and the propagation of a hole together. This gives you 4 places in space, spin, and time, because electron going from A to B and hole going from C to D, 4 places. This is an equation that has 4 arguments in space, spin, and time. In TDDFT, you have the response function, which is a quantity that depends on 2 arguments in space and time and spin if you want. So it's a much smaller equation, which also means that you get less information, okay? You get only the diagonal of the full electron-hole correlation function. So in principle, you have less information, but this less information is what you're heading for in spectroscopy, and it is in principle exact. Then comes the question, what is better, in the sense that what is easier to approximate, or where do I have better approximations, and also what is easier to calculate. So given a relatively simple approximation, the solution in TDDFT is easier than in Bethe-Salpeter, just because it's a reduced problem. To find a good approximation, experience shows that it has been easier for the Bethe-Salpeter than for TDDFT. And the reason is, I think, on one side, the existence of straightforward perturbation theory, and on the other side, this thinking in terms of particles, of electron and holes, makes it easy to intuitively say, yeah, they interact via spin-Coulomb interaction. Yeah, I can imagine what's missing. Whereas in TDDFT, where everything is so compacted, it's very, very difficult to get the feeling. And therefore, absorption spectra in solids is clear. Bethe-Salpeter, now, if you want a parameter-free calculation, is superior. Not necessarily for loss functions.
Okay, thank you, Lucia. I think there would be other questions to ask, but we need to keep within the time. That was very beautiful. So I think we're going to take a 10 minutes break to reflect, and then we'll start with our last lecture from Professor Steve Louis. So I would say there is no need for you to log out, but we'll just take a little break of less than 10 minutes and see you in a moment. And thank you all again. Great. So welcome back, everyone. And again, it's a very great pleasure to introduce the third speakers for today, Professor Stephen Louis from the University of California, Berkeley, and the Lawrence Berkeley National Lab that will be talking about understanding excited states from first principles, single and multi-particle excitations, and time-dependent phenomena. Steve received his PhD in physics from the University of California, Berkeley, and then moved to the IBM Watson Research Center and Bell Labs, clear example of, industrial research at its finest. And then he joined the University of Pennsylvania. From there, he moved to the faculty at UC Berkeley in 1980, where he's not only a professor of physics there, but also a senior faculty scientist at LBNL. Is a member of the National Academy of Science, the American Academy of Arts and Sciences, Academia Sinica, and a foreign member of the Chinese Academy of Science, fellow of the APS, AAAS, and the MRS. Particularly, he received the Anizur Rahman Prize from the American Physical Society and the Davison-Germer Prize, the Materials Theory Award from the MRS, the Forsyth Institute Richard Feynman Prize, the DOE Award for Sustained Outstanding Research in Solid-State Physics, and there are so many other sort of prizes and nominations that I think I should actually give space to his research. So, Steve, we are so happy to have you here. Very warm welcome, and I guess good morning from the West Coast. The floor is yours.
Yes, good morning from California. Nicola, thank you very much for the kind introduction. So let me share my slides. Okay, let's see. Okay, so in this talk, we're going to continue our discussion of using many-body perturbation theory to understand excited states from first principles. So in this talk, besides single and two-particle excitation, we're going to also look at correlated multi-particle excitations and time-dependent phenomena. So let me say a few words about the problem we want to address. As already emphasized by the previous two speakers, understanding materials properties is really an n-particle problem with n quite large. So this problem is impossible to solve exactly, and also is very often undesirable to really get the full solution because they would be so complicated. So it's much better to consider some physical quantities that is closer to your experimental measurement and property of interest, so that one could make approximation to it. So if one were to be interested in single particle like behaviors, say in a transport, tunneling, or angle result photoemission experiment, the appropriate quantity to consider is the probability of finding a particle at position R and time tau if there's one created at position R prime and some earlier time, say at t equal to 0. This, of course, is the single particle Green's interacting Green's function that was discussed in the last two talks. And once you know this interacting Green's function, as we heard from the last two talks, then you could look at the number of property related to single particle excitation in a material. This is what we call an n+1 particle problem. And if you're interested in optical properties, then you would be looking at the n+2 particle problem, which is the right quantity to look at. It would be the two-particle Green's function. So let me say a few more words about excited states in materials. As you all know, excited state phenomena such as transport, optical energy transfer in a material often give rise to its defining attributes, whether it's a semiconductor, metal, or superconductor, and determine its usefulness. compared to DFT kind of calculation, ab initio calculation of excited states often requires a different treatment of many electron interaction effects. There are now exists ab initio methods and computer codes to predict and understand 1 and 2 particle excitation experiments. Sorry, my phone went off. That one could now look at 1 and 2 particle excitations that with increasingly complex in increasingly complex materials. And I listed some of the community codes that is available for researchers to use nowadays. However, there are key phenomena related to correlated 3 or 4 particle excitations, field-driven time-dependent processes, nonlinear spectroscopies, and so on, that are remain to be addressed efficiently by ab initio methods and public domain software, which would include the relevant and accurate many electron interactions. So this is going to be the outline of my talk. I will begin with a bit more discussion on many-body interactions and excited state phenomena in materials. And then we move on to look at correlations in quasi-particle excitations, optical responses, and multi-particle excitations. Then we're going to look at time-dependent, field-driven, and nonlinear phenomena. And then as a last topic, we're going to look at correlation enhancement in the electron-phonon interaction going beyond DFT. So as already discussed in the past 2 talks, if you want to look at the quasi-particle excitation in the material, then the important quantity is the self-energy of the quasi-particle. That is, the particle now interacts with the excitation in the system, and it will modify its energy dispersion relation through a term we call the self-energy. And this term, we normalize the energy dispersion relation for the excitation, give rise to finite lifetimes and also satellite structures, as Lucia's already discussed in some detail. So if you say interested in looking at the probability of finding a particle-like excitation with certain wave vector k and frequency or energy in your material, then it's related to the self-energy through expression look like that, in which the imaginary part and the real part of the self-energy comes in. So this is the self-energy for the 1 particle Green's function, and it has many contributions because you can have many different type of particles in your system that your electron can interact with. For example, electron-electron interaction, electron-phonon interaction. Here we're going to be focused mostly on the electron-electron interaction, and I'm going to touch a bit later on the electron-phonon interaction. Now, if you recall from your many-body physics course, the self-energy, strictly from a many-body perturbation theory point of view, you could write it out in terms of a series of Feynman diagrams. And typically that is done in terms of the Coulomb interaction, the bare Coulomb interaction between the particles, the electrons. However, you could also do partial summation of the diagrams and expand this series for sigma in terms of the screen Coulomb interaction, that W, that is the Coulomb interaction screened by the dielectric function of the system. The idea here is that the screened interaction will be weaker. For example, in silicon, the dielectric constant is 12 actually, And so the interaction will be order of magnitudes smaller than that of the bare interaction. Then one could hope that the series would converge much faster. And this kind of concept is first recognized by Hubbard and Jim Phillip in the late 50s and the early 60s. And the GW approximation that you hear about is basically taking this first turn in this series expansion. And Hedin formalized this through his equations and work out the consequences for the electron gas in the mid-60s. And Hyverson and Louis were able to actually apply this kind of concept to do ab initio calculations for real materials, not until the mid-1980s. For the optical properties, then you could use similar ideas to look at the two-particle Green's function and solving a set of effective equations to get out the two-particle correlations and therefore the optical properties of the material, including excitonic effects. So if I look at the Dyson's equation for the quasi-particles, which has been introduced in the last two talks, then the equation you need to solve is this one, with the solution being the quasi-particle excitation energy in your material. Within the GW approximation, then sigma is given by this convolution integral. W is the screen Coulomb interaction, and G is a Green's function that you could construct from some kind of mean field solution. So here, the idea is that you do the perturbation to some mean field that's close to the realistic solution that you are looking for. So the starting mean field could be a range of different things, as already discussed by Rex earlier. So to carry out this kind of calculation at the G0, W0 level, then you need the full dielectric matrix that comes into construction of the screen interaction, including the off-diagonal element of the dielectric matrix, so-called the local field effects. And then you need some good starting points for the wave function and energy to construct the Green's function. So to illustrate how important screening, non-local and frequency-dependent of screening to the quasi-particle excitations in the system, I show some results here that we obtained for the band gap of silicon. So here's the band gap calculated using the Kohn-Sham eigenvalues within LDA. And then you could calculate this at the GW, G0, W0 level with static screening and no local field. Then you get a gap actually is not much different from the LDA gap. And then if you include static screening, but no local field, then you get a gap, which is much too large compared to experiment. And finally, what this illustrates is that you need to include both dynamic frequency effects and local fields to get a gap that is quite good compared to experiment, actually. Now for optical absorption, then we had to look at correlated electron-hole excitations. So those excitations, because of the electron-hole interaction that Lucia has talked about in detail, the excited state, in fact, is a linear combination, coherent linear combination of electron-hole pairs. And to solve for this kind of excitonic state, one has to look at the two-particle Green's function, solving an effective two-particle equation. That's the beta-salpeter equation. So here are the quasi-particle energies, and K is the electron-hole interaction kernel. So one has to know what this kernel is. in fact, the kernel can be obtained as a functional derivative of the Hartree potential and the self-energy of your system for the one particle excitation. So within the GW approximation, this turned out to be minus W. And so the Coulomb kernel has a repulsive exchange term that involves a big Coulomb interaction and attractive, the normal attractive term that you think about between the electron and hole, but that involves the screen Coulomb interaction. From solving this set of equations, then you could get out the excitation energy and wave function from which you could then calculate, for example, the optical absorption spectrum, say epsilon 2. And this kind of approach has been quite successful over the past decades to look at the 1 and 2 particle excitation of weakly or moderately correlated material, a whole range of them, actually. This is a plot of the theoretically calculated gap versus the experimental gap within G0, W0 for a range of semiconductors. And you see that you get quite good agreement, and then you solve many of the deficiency of the Kohn-Sham gaps. This is a plot of the optical spectrum, epsilon 2, of silicon. The blue curve is when one neglect electron-hole interaction and just use the GW band structure in the interband transition method. Then the red curve is when you include electron-hole interaction. So you see that it's kind of electron-hole interaction give you a dramatic change in the absorption spectrum, even though in silicon, the excitonic binding energy is very small in the order of tens of milli electron volt. So here you could see that the absorption strength can be changed by more than a factor of 2. Now, someone asked how expensive this kind of calculations are. Here I saw a plot of the largest system that people have looked at over the years. In the mid-80s, when we first did the calculation on semiconductors, we could really only looking at system with about 8 electrons per unit cell. But over the years, there have been lots of improvement in the methodology and computer codes. And you see that nowadays we could look at systems with close to 12,000 electrons in it. Here, this particular calculation is for a die vacancy in silicon carbide. Now, to illustrate the importance of non-local screening and correlation, let me give you one example. This is the quantum level alignment at the interface. For example, you take a molecule and move that molecule, say, to a metal surface or a dielectric surface. What you expect is that the molecular level will be modified as it approaches the metal. Here, I consider the HOMO and the LUMO level. In general, there will be several physical effects going on. You could have interfacial charge transfer, so dipoles are set up, or you could have quantum mechanical coupling, a hybridization between the orbital and the metal. And then also there's going to be self-energy electron correlation effect to modify, say, the HOMO-LUMO gap. Here I show you one example, which is benzene on graphite. Here is a plot of the HOMO-LUMO gap when benzene is on graphite at a distance about 3.5 angstrom away. And what one finds is that the HOMO-LUMO gap at the DFT level, it is the same whether it's on the surface or in isolation. And that's because the molecules at the van der Waals distance away from the surface, and there's hardly any wave function overlap. On the other hand, when you look at a GW calculation for this HOMO-LUMO level, what you find is that you have a gap that's bigger than the Kohn-Sham gap, as expected. On the other hand, if you look at the isolated benzene molecule, then the HOMO-LUMO gap at the GW level is actually at 10.5. So there's a 3 eV reduction in the gap due to the fact that it's next to this a metal, and this 10.5 is in fact in isolation for isolated molecules pretty close to the experiment. So relative to the gas phase, the gap narrowed by 3.2 electron volt, and the Kohn-Sham orbital energies do not capture this kind of change, which is not surprising because there's no wave function overlap. In general, change in the self-energy can give you a very large change in the HOMO-LUMO gap, and it's environmental dependent. So here's some more calculation on benzene, but putting it in different surfaces. And you could see this is a work by Garcia Lastra in Lubio's group. And you see that that if you do either LDA or hybrid functional and look at the Kohn-Sham gap, then there's hardly any changes to the environment for the molecule. But for the GW calculation, you see that there's significant changes. Even more interesting is that you look at benzene on 2 different phases of barium oxide, you could have a different, significantly different Kohn-Sham gap, HOMO-LUMO gap. And that's because one of this surface actually have a metallic surface state. So this illustrates that there are strong and different renormalization on molecular level on different substrates that that are absent in Kohn-Sham orbital energies. To illustrate this some more, let me look at the property of quasi-2D systems. We know that in reduced dimension, you have enhanced Coulomb interaction, but you also have very strange and strong spatial screening dependent also. This is illustrated in this cartoon here. 2 charged particles in a 2D system interact through the field lines. So you see that in general, at a very small distance, you would not expect strong screening. And also at very large distance, all the field lines are outside of the sample, so there will not be screening. So a 2D material, you look at the effective dielectric screening as a function of distance, actually have a shape looking like this, peak at some distance related to the thickness of the film, but it's very, very different from 3D, and that gives rise to very strong electron-hole interaction effects. And also environmental screening is important, as illustrated in this example, where you put a 2D material on a substrate, then the field lines go into the substrate and help to screen the interaction. So let me just show you one example, which is the optical spectrum of monolayer molybdenum disulfide. Here is the band structure of moly disulfide monolayer. The gap is a direct gap at the K and K prime valley of the Brillouin zone. And there are 2 series of interband transitions, A and B. If you look at the absorption spectrum calculated within the GW beta saltpeter equation approach, then the dash curve is the absorption in absolute percent when you neglect electron-hole interaction. And with including electron-hole interaction, you see that the spectrum now dramatically changed. You have a series of peaks here corresponding to excitons and excited state of excitons for this kind of A and B transition. And also you get very high energy excitons from other part of the Brillouin zone. And another very interesting effect is that because of the electron-hole interaction, you wrap a lot of oscillator strings from high energy and go into this low energy regime. The exciton binding energy, in fact, is a big fraction of electron volt. This kind of picture agrees very well with an experiment. You see the two lowest energy peaks correspond to the lowest energy A exciton and B exciton over here. And then there's a lot of absorption strength at highest frequency correspond to the excited state of the excitons. And if you include lifetime effects for the quasi-particles due to electron-phonon interaction, then you could even have a better agreement between theory and experiment. So electron-hole interaction, in fact, dramatically changes the property, optical properties of 2D materials. In fact, the change is so large that a monolayer moly disulfide could absorb 20% of the light in this kind of frequency range. Now let me say a few words about substrate screening. The example I give here is for monolayer molybdenum diselenide on top of bilayer graphene. What's shown here is if I put a point charge in the moly diselenide and ask what the extra induced screening due to the substrate is, this is the induced charge. So it's quite complicated because screening is non-local and frequency dependent. So to incorporate this into the spectroscopy of the property of the excited state of the system, you really need to include the substrate screening. In fact, for some systems, substrate or encapsulation of the 2D material can renormalize the band gap, the intrinsic band gap of the material by more than 50% and change the exciton binding energy by a factor of 2 or more. And also it could modify other excitation in the system, for example, plasmons in this kind of system. Now let me turn to the non-equilibrium and beyond 1 and 2 particle excitations. Now, to understand those phenomena, we had to go beyond the standard ab initio GW and GW beta salpeter equation approaches. For example, if we're interested in biexcitons or trions, then we really have to solve now the interacting 3 or 4 and 4 particle Green's functions. And if we're interested in time-dependent phenomena, such as pump probe measurements or nonlinear optics or field-driven transformation of your system, then we have to actually look at the explicit time propagation of the Green's function in presence of some driving field. And here we now have to look at the time-dependent Green's function, say in the GW approach, using a non-equilibrium Green's function formalism. Now, because Coulomb interaction is stronger in reduced dimension, it's not surprising to see that multi-correlated multi-particle excitations are more prominent in atomically thin 1D and 2D systems. The example I give here is the case of biexciton on monolayer tungsten diselenide. What's plotted here is the luminescence intensity. These are experimental curves. And what you see here is a peak labeled by XX, which increases with the increasing excitation light intensity. This peak has been identified as a bi-exciton in the system and is well studied by experiment. And this kind of excitation is what we would like to understand. And they are actually of fundamental and practical interest in other areas. For example, exciton condensates and the splitting of a single exciton into two exciton in organic crystals for photovoltaic applications. Now, as we already discussed, to arrive at quasi-particle excitation within the GW approach, you have to solve one Feynman diagram like this one. To get the optical excitations in the GW beta salpeter equation approach, you need to solve two Feynman diagrams. For bi-excitons, because you now have 4 particle excitations, you actually now have to solve a 36 diagram of this type, which involves 4 particle lines. And actually now this is doable. Very recently, we have developed the methodology on and also the computer codes for doing such calculations. Here, let me show you some examples for the case of atomically thin 2D tungsten diselenite. This is a 2D semiconductor similar to moly disulfide with a band structure looking like this, which is a direct gap at K and K prime, very similar to moly disulfide. The band structure at K and K prime looks something like this. The states are kind of a time reversal pair of each other. You could form a bright intra-valley exciton, like the ones I shown here, or a dark intra-valley exciton, like this one where the spin is flipped. And also you could form dark intervalley exciton like this. These are all low energy excitons in the system. If one of these excitons capture an electron, then it becomes a negative trion. If 2 of them combine to form a bi-exciton, then to combine to form a bound state, then it's a bi-exciton. So here,
I'll mention also the 30 minutes mark.
Okay, sure. I'm trying to finish up in 2 or 3 minutes. So the bi-exciton and trions, this is some results that we have for monolayer diselenite. You see these are the binding energy for trions and bi-excitons. The calculation gives a very good agreement between theory and experiment. This is actually the first fully ab initio many-body calculation on n+3 and n+4 particles using many-body perturbation theory. Our results show that you have very rich energy and spin and valley level structure for this kind of phenomena. And that actually helped to really understand the experiment, because previously bi-exciton in this system is thought to be of this type, intravalley bright exciton combined with the intravalley dark exciton. But what we find is, in fact, that this measure bi-exciton is an intravalley bright exciton combining with an intervalley dark exciton because of important electron-hole exchange effects. Now, let me show you a couple of results on time-dependent phenomena. Here, you need to solve the time-dependent of the Green's function in the presence of a field on the Caldas contour. And the method we use is ab initio time-dependent GW method within the adiabatic approximation, very similar to the adiabatic approximation in TDDFT, and with real-time propagation of the density matrix. I will show you a couple of results. One is shift current in monolayer germanium disulfide. Shift current is a second order process, optical process, generating DC current from AC applied field. Here's just some quick results. This is just to, this plot shows one of the components of this shift current tensor. And what we've shown is that electron-hole interaction could enhance this shift current by orders of magnitude, because in 2D materials, excitonic effects is very important. And similar kind of change also occurs in second harmonic generation and so on. Another thing we could look at using TDGW is to look at field-driven phenomena, say in time resolved, angle resolved full emission experiment. The idea here is you pump the system with a pump optical light to excite the system to a non-equilibrium state, and then you probe it later. It turns out that you could learn about excitonic states of the system using this kind of a pump probe technique. Here's some results we have for the case of monolayer germanium sulfide. This is a result without having a pump. And then this one is with a pump that has frequency corresponding to excitons in the material. And you now see that there are actually extra features in the angle resolved full emission experiment due to the excitons. And from reading the position of the states, extra states, and the width, you could learn about both the exciton energy and the wave function of the exciton in K-space. I won't have time to talk about this in detail, but I will glad to answer some question on that you asked. And then as a very final thing, let me talk about electron-phonon coupling. And of course, this is a very important interaction in materials. Within DFT, what you really calculated is the interaction of the Kohn-Sham electron with the phonon. And that has been very successful for many materials, but it does fail for some materials. So what we have done lately is to calculate electron-phonon coupling at the GW level. Basically, what you do is replace the term that involves the exchange correlation potential in DFT by the term involving the self-energy within linear response theory. What we saw is that this kind of correlation effects can change G by as large as a factor of 2. For normal metal DFT and GW electron-phonon coupling, it's very similar. But for some of the oxides, they could be different by a factor of 2. And for example, in this system, barium bismuth oxide doped with potassium, it could change the superconducting transition temperature by orders of magnitude, and you cannot explain that with DFT. So let me conclude with this last slide. I hope I have shown you that, as already the previous two speakers have shown, that many body interactions are centrally important in many material properties and phenomena. The treatment of interaction effects at the appropriate level is essential, especially for excited states and low dimensional system. Many body perturbation theory with the screen Coulomb interaction is a powerful approach for looking at excited states in materials. So let me stop right here and just acknowledge the funding support for the work that I talked to you about. Thank you for your attention, and I'd be glad to answer questions.
Thank you, Steve. That was wonderful. And we have questions in the question and answers. And again, people are also welcome to raise their hand. Maybe again, I'll get started. And this, low dimensional systems had really given the opportunity to see this, 2 particles or 3 particles effect. But I wonder if at the same time, they make in real life this effect more extrinsic in the sense, it matters so much what surrounds your 2D material, your 1D material, and so you becomes more difficult to predict unless you're in super control conditions.
Yeah, well, it is important to the work of many from both theoretical and experimental work that it has been well established now. The property of a 2D material depends on its environment. And that, in some sense, is great because it gives you another knob to tune, to control, and design the property of the material you want. So I look at it as not from the point of view of having a lemon, but making lemonade out of the lemon.
Thanks. And let me take a question from Gabriele Riva that asks, which is the strategy to calculate the 3 or 4 body Green's function? Is there a recursive equation like the Dyson equation or the Bethe-Salpeter equation?
Yes, exactly. So you have the Dyson's equation, and as Lucia talked about, you have the 2-particle correlation function give you a Bethe-Salpeter equation. You could look at the 3-particle and 4-particle Green's function, and you would end up with kind of Dyson-like equation for the 3-particle correlation and 4-particle correlation function. And the kernel that goes in are the Feynman diagrams that you need to evaluate. So basically, the machinery is very similar. You just have to evaluate those effective 3 or 4 particle interactions and put it in a Dyson-like equation to solve it.
I can't resist asking a follow-up question here because the combinatorial complexity also goes up, and we have seen 36 diagrams, and I think is saturating the life of a PhD student. So I wonder, this is a bit science fiction, but do you think one day computer will code the recursive equations, so that is we stop actually coding ourselves and
yes, well, I have a fantastic postdoc, and he was also a graduate student in my group. He actually wrote the computer program to identify the Feynman diagrams at the level with screen and non-screen interactions. Okay. So those diagrams are actually generated by the machine.
Fantastic. Yeah. Okay, very, very, very good. Let me go another question, Lorenzo Sponza. It says, it seems that a static approximation without local fields, so no local fields cosex, does not improve with respect to, say, LDA. But what about a dynamical no local field approximation? That is, how much important is the dynamic or how much important in this local field? And I don't know if, this question can be answered, but does a no local field GW perform well?
With dynamic and no local field, there was some work that done by Wang on making a local approximation to the self-energy, and it does not give you a quantitative result. I've forgotten whether it's up here or down here. I forgot what it is, but it's certainly not at the level of including both dynamical effects and local field into the calculation.
Thanks. And we have an anonymous question that is asking, why is screening not effective when the electron and the hole are at a distance that is much smaller than the film thickness?
Oh, okay. Maybe going to this diagram would help. So
you probably have to share the screen.
Oh, okay. Sorry. Okay. So the question is, so why is epsilon equal to 1 at small distance or large distance?
Yeah.
So at small distance, it would say the plus and the minus charge are very close to each other. There's no other particle in between. So screening just become 1. The dielectric function is 1, just like if you have a very large Q for any kind of system, epsilon of Q going to infinity is equal to 1. On the other hand, if the distance is very large, then the field line go outside, so it becomes 1. So it must peak in the middle, and then that's this diagram. This is actually a full calculation.
Thanks. And there is another question from Lorenzo Sponsor that says, now the application of GW to large and realistic system that you have shown, or there was that graph. Is it possible because there have been algorithmic improvements, or is just progress in the hardware?
It's both. There's certainly lots of algorithmic improvements, both treating the frequency dependent of screening and calculating dielectric functions and so on, and also there are kind of algorithmic improvement in terms of how to calculate those quantities using fast Fourier transforms and so on. And of course, there's also machine improvements over the years. So it's a combination of both.
Great, thanks. Steve, I think I'm afraid I probably have to stop here this presentation because we have a hard cutoff that I think is good for everyone at 7 p.m. and also I know you and the others will have to leave. So maybe I would ask everyone to join me in a round of virtual applause for these 3 presentations. It was great to hear them live and great that they are recorded for everyone that is new. And so we would like, as we usually do here, to spend the last, we have less than half hour with all of you, with you, Steve, but also with Rex, with Lucia, there is Ignacio and Sarah, and we make it into, a leisurely conversation. And again, it would be nice to keep also the audience involved, so people are very welcome to join in with questions on the question and answers that we don't really make them, scientific. We have covered the science, but this is more about, I would say, the scientific process. And so I usually get started, and maybe we do it, let's say, chronologically, quote unquote. But so I'll start with Steve because I feel it's interesting for all of those that are listening to also give a bit of a perspective on, how was it and how were things different when you started doing research? I mean, would you have forecast, where it would have gone? And, what was better and what was worse and what was different? So this is a bit, an occasion. And maybe I'll give it to you, Steve, and then to Rex, and then to Lucia.
Okay, I think, I started in the early 70s, and this is the time where the electronic structures just start growing, the calculations and so on. So I think there have been a lot of progress over the years in our field due to many people, of course. And I think when I was a young researcher, doing computational physics does not have the kind of respect that we have nowadays, because a lot of people still don't believe in it, and also there's this misimpression that computation is mindless, and you don't make conceptual breakthroughs and so on. But obviously that's not true, and that's why I went into the field. And And I think, you know, nowadays, if you put in a proposal for funding to do a research project, very often they would like to have a theoretical computational component. So it's a huge change for our field. I don't know what I answer your question.
No. This is actually, I had forgotten exactly how difficult it was to fight for the field sort of some time ago for yeah. And actually, it's interesting. I'll take a question from the question and answer, because actually, instead of these days, you know, what is called the black box machine learning seems to be all the rage, and it even gets all the respect. So isn't that somehow strange how much things have changed?
Is that question addressed to me?
Well, I mean, I think it's just that I thought it was interesting to see how exactly computational physics was somehow maybe criticized a long time ago, because the comment was that you wouldn't really understand what is going on. And nowadays we have sort of completely moved to the other side, and you know, there is a sort of blind faith in machine learning. But I let also Rex and Lucia comment on sort of, you know, their experience entering into the field and what has changed for better and for worse.
Yeah, well, certainly the change in computer power over the period is just absolutely astounding. I was looking at some numbers the other day and looking at the computer, for example, that we used to do our first GW calculations at Bell Labs, which was the Cray XMP. This was from memory, I think it was about a £4 or £5 million cost to buy a Cray XMP, and yet it had speed and memory which was 4 or 5 orders of magnitude down on an iPhone today. It's just incredible. While of course agreeing with Steve that algorithms have improved, it sometimes strikes me that what we're able to achieve in computational condensed matter physics hasn't perhaps quite as advanced as fast as one might expect, given the improvement in computer power.
But we are, I would like to add that, but we are working on much more complex phenomena than, you know, 30, 40 years ago.
Yeah, that's true. And I think it also reflects that when a field is young, people are very ambitious, and they try to answer questions that are not quite within the grasp of the present tools. I was looking at some of our workshops in Europe, often held at the old CCAM in Orsay, with contributions, for example, from Lars Hedin, Rodolfo Del Sole, and so on. And the titles of their talks are talks which, in my opinion, would still be interesting to go to today. So things don't necessarily move on all that fast.
That's why we record you, but let's see Lucia what she thinks.
Yeah,
and
maybe
Sarah also welcome to chip in.
Maybe I jump in here with an anecdote, because I started in the mid-80s with my PhD, and concerning ab initio GW calculations, I started with Rex. Actually, Rex told me to do ab initio GW calculations, and when I wanted to move from silicon to cubic gallium nitride, Rex, I don't know whether you remember, but you said, "Are you crazy? You will never be able to do that," because it sounded so absolutely out of reach, right? And it's true that I had to lie whole nights on the floor with this modem, which was connecting to the Cray computer and which has a lot of little lights on it. And from time to time, I would have to hit it because it would give up otherwise. And so it was really very different. But there's another aspect that that you brought up, which is that the field has been moving from a pioneering environment where one was super crazy to something more established and maybe more business-like. And this has good side and has also bad sides. I think we have to really strive to do more than business and keep this pioneering character. And maybe I would also like to add the general environment, which I think has also improved in some ways and worsened in some other ways. Has definitely improved. I mean, me as a female scientist, I must say that I found it quite tough in the 80s when I started. This was not a very female-friendly environment, and I think this has improved a lot. On the other side, we have a lot more pressure now to publish quickly, to deliver results quickly. I don't know in the US whether this has changed, but in Europe has definitely changed. And this is not pushing you to take risks and to invest in really completely new and crazy things. And that is a pity.
Yeah, that,
I agree.
Sarah, please.
First of all, thank you very much for this. This was a wonderful afternoon. I just wanted to go perhaps a bit deeper on something that Lucia mentioned during her talk. I mean, you said at some point that there are moments when ideas are in the air and topics are sort of ripe for progress and ideas are shared from different groups and so on and so forth. I was wondering if you and Rex and Steve could sort of comment a bit on this, just give us an idea about how it felt, why it felt that that was the right moment and how this sort of came about. How was communication among groups? I thought that that was an interesting point for me.
Maybe I can start because I think it was CCAM played a huge role here. Because the workshop certainly showed you that
fishing for compliments here. Sorry.
No. But this was the place where the workshops were held, and this was the place where someone said, "Oh, I'm going to try this," and maybe have preliminary results, and then someone else would say, "Oh, yes, this is absolutely to be done." And we also started the European networks, which I think was very important, because this was really a way to collaborate. I think it was true collaboration. And Steve, you would correct me if I'm wrong, but some colleagues from the US asked us, how can you collaborate in such a way? It was not so much in the sort of not so usual in the US to have these collaborations. And I think it gave us a lot of strength, and in this make of course ideas diffuse extremely quickly. And then we had something like friendly competition, right? You see your friend doing something, you want to also do it.
Yeah, I agree. I think that something like the Psyche network is really unique, and that it didn't happen in the US, and I give you guys a lot of credit for building that up and get everybody together to look at important problems. But certainly, sorry.
I was just going to say, unfortunately, the European funding model now is such that it's actually generally not possible to get collaborative research networks funded anymore. The Commission is looking much more on projects that are directly orientated towards industrial needs.
Yeah, I think there is a long discussion. We have had some in the Marianne Mansai conversation, and I think we'll have more about the relation between sort of industry-driven research, sort of science-driven research, and so on. A few more, we don't have much time, so I want to go over some of the other things. That is, I wonder if you have had role models or teachers of people that have really left an impact in your scientific life and have, taught you or driven you in interesting directions?
Well, I could say a few things about that. I think I mean the work that that we did in the 80s, early 80s, to started working on this ab initio GW is really a major contributor is Mark Hyberson. He's actually my second student, PhD student at Berkeley. When I first joined Berkeley, I started building up a group. My first postdoc is David Vanderbilt. First student is Chi-Ting Chan, who is now a leader in metamaterial physics. And Mark is my second student, and then my third student is Stephen Fahey. So some of you know him. So having a really good environment at Berkeley has helped my career a lot. And then, of course, I have a lot of mentors over the years. Anticipating this question, actually, I like to show one slide. If I could share the screen. Let's see, could I share that now? Yes. That is Mark Hyberson right here. He did all the work as a graduate student with me on this project. The people really influenced my life are this four gentlemen right here at the bottom of the slide. Marvin Cohen, who was my thesis advisor, and Jim Phillips really was a mentor to me in my early career. And his screen exchange paper influenced me a lot to look into Herdin's equations and beginning to work on the GW approximation. So Jim is the thesis advisor of Marvin Cohen, and Maura Cohen was a thesis advisor of Jim Phillips, and then Charlie Cattell was the thesis advisor of Maura Cohen. So these four gentlemen actually really were the mentors to me in the 70s and 80s that teach me all the things that I know, and the more important thing is teach me how to choose problems and work on the right problem and have a good connects to theory.
Thanks, Steve, and yeah, choosing the good problem. And I'll give it to Rex and Lucia, but also your words, reminded me the advice that I always give to new graduate students. Work with a junior faculty member, because his career or her career depend on what you do, and you'll work, very closely, and you'll do some of the nicest stuff together. But Rex and Lucia, what about you? What about role models or people that have left an impact in your scientific career?
Well, I'd like to mention Michael Schluter, with whom I worked at Bell Labs. This is where I got into this GW stuff for the purpose of investigating density functional theory. I think he was a good embodiment of the sort of Bell Labs spirit, which was extraordinarily aggressive in some ways for somebody coming from England, but at the same time extremely productive, interested in both fundamentals and applications, and in a great hurry to make progress. I'm sure he picked up a lot of that attitude in his time at Berkeley, Steve, earlier before he went to Bell Labs. I'd also like to mention Lars Hedin. We've heard his name mentioned many times. He was a true gentleman scientist who was extremely modest. I've only recently really come to recognize how far ahead of his time he was with his work in the 60s. And he was always very, very helpful in our workshops to discuss possible projects. I'm sure Lucia and Steve, you'd agree with that.
Yeah, maybe I can add to that in his 1965 paper, we often cite this in the abstract. There is written there is not much new in this paper, and it was really, really so important paper for us. And if I should maybe continue, I personally, I mean, I won't cite many names because there are many people who have really influenced me and really taught me and really helped me. But if I should say what kind of people, I would say this is exactly people who made me feel well. So I would exclude the very aggressive people. For me, it's very important to feel that I'm at my place, that I'm accepted. Otherwise, I cannot learn. And I had I was so lucky with my master's advisor, Ivan Egri, and then PhD advisor, Rodolfo del Sole, whose name has already been mentioned, and who really made me feel like a colleague, scientific colleague, and we just had fun together. I mean, it was just this feeling that we want to know it, you know? It was not about writing many papers or so, we just wanted to know it, and this was extremely important for me. And this continues then. And then maybe another also important thing is people who pushed me out of the comfort zone, who made me think about things I always put under the carpet because I was lazy and found it difficult. For example, when we were writing the book with Richard Martin and David Sepperly, not only they made me feel comfortable, but they also pushed me out of my comfort zone, and I'm very grateful for that. So I think these are two important things.
And thanks, Lucia. And for each of you, do you have I don't want to call it a eureka moment in terms of a discovery, but are there moments where that you remember where you sort of realized that maybe the field is really having an impact, or is it a continuum of discoveries, or there has been a moment that you go back fondly and you think, oh, that day I felt that there was finally something important happening?
What you call an impact? Is an impact on technology? Is it a product, or is it like understanding?
Can be understanding, can be relevance, can be, finally we can, study something real and realistic, and, some might find comfort and excitement in that, and some no.
Like seeing the first ab initio beta salpeter result and seeing agreement with experiments is great feeling, yeah. Yes.
Well,
but it's also the understanding, right? When you really manage to understand something, that's also absolutely great Eureka feeling, I think.
Mm-hmm.
Steve, for you?
Yeah, for me, it's I think it's more a continuous progression. You tend to build on what you learned. I started with kind of empirical pseudopotential approach, getting understanding of experiment using some empirical fitting parameters. And then, when DFT comes along, we learn how to calculate, dielectric matrices and local field effects and so on. And then the band gap problem comes up, and then you start putting those things together and try to attack that problem. And then you have the kind of previous knowledge and start building on it. And So it's a lot of fun. That's a function of time that you beginning to put, like building a big monument, then somehow you're able to get better looking and a more pleasing results out as a function of time.
Yeah. And your X, did you have sudden illumination, or is more?
Well, I think it was more possible to have a sudden change of feeling about one's own work in the days before the internet, because now we have so much information at our fingertips. We can contact people all over the world with ease. It's pretty obvious from an early stage where a project, if it comes out in the way that one hopes, is going to sort of fit into the furniture of science. But back in the 80s, the early 80s, when I was a PhD student, of course, that wasn't the case. One was working pretty much in a vacuum until maybe one published one's first paper, and then got those postcards through the post that said, "Would you please send me a reprint of your paper," which was pleasing. And also, I would mention the big conferences were so much more important than they are today in allowing you to sense how your work fits into the general framework of science. So I would cite, for example, when I presented the work that I did at Bell Labs at the APS March meeting. I think it was in Las Vegas. And I suddenly realized that, yeah, okay, there are quite a few people interested in this, which was nice.
Yeah, thanks. I think we are coming to a close, and I know that Steve has to leave at 7 sharply. So there is the last mystery question, and I'll ask very quickly, and inspired by the BBC Desert Island. So we are going to strand you on a desert island, and you can bring only a book and a record that this day will probably be a Spotify playlist. So I'm going to ask the three of you, what book and what record would you bring with you on the desert island? Steve, you have to go first because we know you have to leave. You're muted. Sorry, I muted you because there was some echo. So you have to unmute yourself. Apologies. Yeah.
Oh, well, it's a tough question. I guess, I don't know what the right answer for me is. I think I'm at the stage of my career that I'm getting old and forgetful. And so I probably will bring my own book and try to remember things and then start working on stuff.
What about the music? Because I guess you don't have a record to your name.
Yeah, I don't have a record on my name, but I could do consider my records would be one of the Beatles records.
Fantastic. And you, Rex?
Yeah, well, the music is very, very easy. I'm a keen choral singer, and like all good physicists, my favorite composer by a mile is Johann Sebastian Bach. So I would vote for the B minor Mass by Bach. It really has everything that one could want for in music. As for the book, I think that's quite easy. There are so many sections in this book that I keep meaning to read and want to get down to it and to read. So this will keep me going for a while on the desert island.
A little bit of advertisement here, and Lucia, it's your turn to close this conversation.
Okay, so since I know the book by heart, I would not take it with me on the island. I'm not sure on the island I'd like to do physics. I think I would take like book by Bulgakov, Master and Margarita, or something like that. And for the musics, I very much agree with Rex, but it's getting boring. So I would take maybe a Beethoven symphony, like the 9th Symphony of Beethoven, I think.
So we close with the Ode to Joy. It was really a great pleasure. Apologies, we can't stay longer. This conversation are wonderful, but we need to be respectful of everyone's time. You can see yourself recorded soon for posterity, and everyone has asked about this. I just have to thank you on behalf of Sekam and Ignacio and Sarah for this wonderful afternoon or morning or evening for many of you. Thanks.
Thank you.
Thank you very much for the opportunity.
Yeah, it really is the best seminar format I've ever come across. Fantastic. Thank you.
And they will even pay us holidays on an island.
Thank you, everyone, also back home,
Thank you.
and keep in touch.
Bye-bye.
Bye, everyone.